My research is on using multi-objective optimization methods for mesh untangling and also mesh quality improvement for quadrilateral meshes, the specific type of meshes. So let's start with some definitions. What is a mesh? Why do we need meshes? So a mesh basically is a collection of nodes and cells, which we call elements, put together to represent a geometry. That geometry, let's say you have a geometry, you want to model that in a computer system. So you use meshes for that geometric representation for your computer system. Why do we need them? Well, I assume all of you have watched animations or movies with special effects or played some video games. So all of the objects, characters, environment, everything that involves a computer-assisted programming, a computer-assisted geometry representation, these are all made possible by application of meshes. And a more engineering example of that would be, let's say you're an engineer, you're working for an aircraft company, they want to design a new model, you want to see how the new model performs if it is put into some, turbulence conditions. So you need to solve, in order to find, for example, the pressure distribution on this new design of your aircraft, you need to solve a partial differential equation, which is a class of differential equations. And you need to solve them numerically. Well, if you want to solve them numerically, you need to have a discretized domain. That discretized domain is obtained by dividing that domain, for example, in this picture, into these smaller cells. As you can see, these are like triangular faces, and then solve your equation on those domains. So that would be an engineering example, an engineering application of meshes. Now, with that said, we have different types of meshes. In general, all meshes are polygonal meshes. If you narrow our focus to 2D, two main types of meshes are used, triangular ones and quadrilaterals. We also have a combination of different classes of meshes to be used for geometric representation. Whenever you use a combination of two types of different methods, as is the case in figure 5, you have what is called a hybrid mesh, which is basically a combination of different types of meshes. Now, we talked about meshes. We talked about why do we need them? What are they? Different types. But when we're talking about meshes in general, we want to have good quality meshes. We want to have an accurate representation of our geometry, whether it's for animation, whether it's for engineering applications. And how do we make sure that we have good quality meshes? The question is, does ever a bad mesh happen? The answer is yes. For example, in car crash simulation, you have a very well-designed mesh, but after the impact, all of those elements that represent your geometry are going to be overlapped, are going to be tangled. So that's an example of a bad mesh. On this figure, we have three main classes of these non-ideal elements. So first class would be the explicit tangling or the explicit overlap between elements. These are examples of that. You see how these elements are overlapped with this one, how these elements are overlapped with that one. So these are explicit tangling. We also have implicit tangling, which is the case for this one. The element doesn't necessarily overlap with other elements, but the result of moving this node gives us this shape that doesn't have a very good angles on the edges of that element. So this would be an implicit tangling. And also we have non-smooth meshes. That element at the top left corner, which is a little bit dislocated, that would be an example of non-smooth meshes. So we have three classes, three different types of non-ideal elements: explicit tangled, implicitly tangled, and non-smooth elements. With that said, how do we identify these elements without looking at the picture of the mesh? What if we are given a bunch of numbers, bunch of values, and then we are asked to determine whether we have good quality elements or non-ideal elements? Well, for that we have quality metrics. So what are quality metrics? Quality metrics measure the quality of our elements. And we have a large number of quality metrics. In this work, we use these 4 quality metrics: the area, the aspect ratio, radius ratio, and escape Jacobian. Also, quality metrics have different types, 2 main types. They are geometry-based, which are these 4 quality metrics that we use in our work. They are also solution-dependent, which we do not use since the majority of the work are using geometry-based, and we want to use geometry-based to see how our method fares against other methods in the field. Now, so let's say we have a mesh that has non-ideal elements, and we want to improve that mesh, the quality of that mesh. We want to get rid of those non-ideal elements. So how do we do that? Optimization offers us a hand to use in improving the quality of our mesh, getting rid of those tangled or overlapped elements. And there has been efforts to use optimization methods for this purpose, but the majority of the work is focused on using a single quality metric for building the objective function. Now, what is the problem with that? Well, those quality metrics that I showed in the previous slide, they have different values. Different set of values for ideal elements, different set of values for non-ideal elements. So if you're using one of them for your optimization problem, and you try to obtain those values for ideal elements, there is a good chance that if you use another quality metric, that quality metric is going to give you non-ideal values for that element and produce a non-ideal mesh, a mesh with not a very good quality. So to address that, we want to put together different aspects of a mesh using different quality metrics for those aspects to make sure that we improve not only one aspect, but multiple aspects of the mesh, so that there would be there would be a compromise between those different quality metrics that are used in the method. Now, what is our goal? Well, we consider 2 aspects. We want to have good quality elements. We don't want to have those non-smooth elements. Also, we definitely don't want to have tangled elements in our mesh. Our goal is to improve the overall mesh quality by focusing on improving the quality of the worst element in the mesh. Because if you focus on the worst element in terms of quality and improve the quality of that element, then overall, you're going to have a good quality in the end. How do we do that? We use a mathematical method called exponential sum method to put together these competing quality metrics into one objective function. And we define our optimization problem as a minimization problem. An example of this objective function, of one of the objective functions, is provided there. That is the objective function that is built by using the aspect ratio metric and the escape Jacobian metric, which explicitly measures the tangling aspect of our mesh. Aspect ratio is concerned with the smoothness or non-smoothness of the problem. Now, once we have the objective function built, we have this non-smooth objective function, meaning we cannot use solvers that are dependent on finding the gradient of the objective function, which could be a good thing, could be a bad thing. Could be a good thing because if you have a solver that can handle non-smooth objective functions, then you can use that solver for smooth objective functions as well, but it's not going to work the other way around. So for that matter, we use a derivative-free optimization solver called pattern search method, which was first used, proposed by the paper that is cited over there. Now, how does this work? It's called pattern search because it creates that pattern, that be a line over each node. And once you're at the current node, which is represented by X sub K, you have 4 candidate locations. Since it's the minimization problem, the solver goes on and evaluates the objective function value at those candidate locations. And then decides between these 4 candidate locations and the current location, which one has the minimum objective function value. Whichever location has that, it's gonna choose that location and move on to the next node. And it's gonna repeat this for all the nodes in the mesh. So here are 2 simple examples of how it works. In the top one, we have explicit tangling. Our pattern is formed on the node that caused this explicit tangling. It evaluates the objective function at those 4 candidate locations. It finds that the bottom location is the ideal one. So it chooses that location, moves the node to this new location, and moves on to the next node. But does it always do that? No. As the example, the bottom example shows, it forms the pattern, finds out that the current location has the minimum value of the objective function. So it doesn't move that node anywhere and moves on to the next node. It does a little thing before moving on, which we're going to touch on the next slide. So next slide, we have the main algorithm for our derivative-free optimization solver. So what it does is that it forms the pattern, finds the minimum. If it doesn't move to the next node, then it says, let's look closer to that node. Let's shrink the pattern. Let's see if there is any location that gives us the minimum objective function value. If it moves to the new location, and as a result of that movement, there is new tangling introduced into the mesh, then it's going to say, let's not move that much. Let's backtrack a little bit so that we don't introduce new problems into our mesh. How does it do that? With these 3 subroutines. So algorithm 2 is the exploratory phase, forming the pattern, finding the minimum. Backtracking phase is when you move into this new location. As a result of that movement, you have new tangling in the mesh. So you backtrack to address that tangling, address that problem. And algorithm 4 shows the updating step, which says none of those problems happen. This new location gives us perfect minimum value for the objective function. So we accept that and we move on to the next phase. So we have numerical experiments, 5 pointed to start before we run in our optimization, and after we have some results here. So the first one, the first plot top left shows us the convergence plot, meaning is there a minimum for the objective function? Do we achieve that minimum? And if we do, are we getting away from it, or are we approaching a certain value? And that plot tells us we found the minimum and it didn't oscillate around that minimum. Second one shows the number of inverted elements, number of elements that are tangled. So after the first pass, we don't have any tangled elements. The two bottom plots are histograms that are showing the number of inverted elements before and after optimization. So the bottom left one is before optimization. On the negative side of this histogram are the number of inverted elements. On the right side, the positive values are the number of non-inverted elements. Before, after optimization, you see that we don't have any more inverted elements or tangled elements. Second experiment, we have this concave domain. We perturb the mesh, run the optimization. Again, we look at the results. Convergence plot doesn't oscillate. Number of inverted elements decrease, went to 0 after the 4th run of the optimization. And also post-optimization, we don't have any inverted elements based on the bottom left graph. We have a femur. We perturb this mesh by introducing this twist at the bottom. Femur is the bone in your thigh. Don't go search the twist in the femur as I did. They're not gonna be pretty pictures. So as a result of that twist, we have two waves of tangling happening in the femur, going up and left. Post optimization, we see that the elements are not tangled anymore. We have the results for that. Number of inverted elements are decreasing. You look at the histograms, there are inverted elements here, but after optimization, the number of elements that have the value of 1, which is the ideal element value, has increased, and also we don't have any more inverted elements. Here's the interesting case. The question is, does this method work on every type of tangle? The answer is no. Neither there are any other methods that can claim that, because there is no theory that proves there is one method that can untangle any type of mesh or any type of untangled mesh. So how do we make sure our method is robust? It works for almost everything. We just have to test it on a huge data set to see how it performs on a big number of test cases. The more test cases it can untangle, the more confident we can be in the method ability to untangle almost everything. So here, this annulus, we twist the middle ring. Before, after optimization, we got rid of that twist in the middle. But if we introduce another twist in the inner ring, after optimization, you can see that the inner ring still has tangled elements there. Now, why this happened here? Well, we have geometric constants here. The inner boundary, outer boundary are fixed. So if you're twisting the inner boundary and fixing the outer boundary, no matter how much you move the nodes in between these two boundaries, that inner boundary is still gonna be remain fixed, because there is no room for moving the other nodes to untangle the tangling that is on the inner boundary. So in conclusion, we proposed a multi-objective optimization method for quadrilateral meshes. It is capable with working with non-smooth objective function, and it can also, you can integrate multiple aspects of a mesh into building this objective function. As future work, we want to test this method on more test cases to raise the level of confidence of the method. And also we want to extend the application to higher order elements, which are elements that have curved edges instead of straight edges. And in the end, we want to thank our supporters in the National Science Foundation who supported this work through these 2 grants. Thank you very much.
Thank you. I have one question, and then we'll go with you guys. Sorry. So you said that you are using pattern search for the optimization part, and you have a multi-objective function, right?
Yes.
And you said the pattern search just search for, it's a derivative theory optimization, is search for local points and chooses the best point in terms of objective value.
Yes.
Right. So now what happens if you stuck in a local objective, or you have some assumption about your objective that is, like, for example, convex or concave or something like that?
Great question. So are you asking if the current node has the minimal objective function value?
No, I'm saying, what happens if you stuck in a local objective and there's no way out of the local objective?
We are not concerned with the global optimal. This is a locally focused optimization.
So it's your application is not important. In your application, there's no difference between global optima and local optima.
No, we're not concerned because this is locally done. That's why we go from one node to one node instead of considering all the nodes in the mesh.
Oh, I see. So you consider every node of the graph or mesh.
Yeah, except the boundaries that are fixed, because we don't want to change the geometry.
Great.
Yes.
Do you have any measure for a tangled mesh? Like you showed examples of something before, and then you showed examples of something after. Is there a measure of how tangled the something before mesh is versus how tangled the resulting mesh is?
Yes, so for that we have the escape Jacobian metric, which if I go to this example, escape Jacobian is negative or 0 for degenerate and tangled elements. And this shows us the distribution of the escape Jacobian value, the value of the metric for all the elements in the mesh. So those negative values and 0 values are degenerate and tangled elements.
Okay.
Yes.
I have a couple of questions. I guess about the derivative free.
Yes.
Really, you are measuring the amount of improvement of your current objective function with respect to your neighbor, right?
Yes.
So somehow you are calculating a delta. I mean,
We're not considering the difference to say. You want to
say
see,
for example, all of them improve, but which one you choose? You choose the one that has the largest delta.
we have 5 values for each node. The minimum of those values is chosen.
Right. So
Yes.
somehow I'm saying that the same concept of the derivative is there, but with the step size of 1.
Yeah, but we don't calculate the gradient.
I mean, you need to calculate the value of your objective function and compare, right? So you have 5 values.
Right. So to answer that, it would be something like you have average rate of change and instantaneous rate of change. Instantaneous rate of change is the average rate when the 2 points are really, really close to each other, right? You take the limit. So here, using that analogy, we are using the average rate. We're not taking the limit there. So it would be the values themselves, not the difference between them. More of a comparison between values than the difference.
Yeah, all I'm saying, I mean, it's kind of somehow mimic the behavior of the descent, meaning that
Yes.
basically you are moving in a direction that you have the most improvement, which is
Absolutely.
somehow saying that.
No, that's absolutely not.
I guess my other question is that, I mean, so you have this objective function, right? But you are doing all of this kind of meshing and all of this stuff to, as you mentioned, for example, to run an experiment or design a new kind of aircraft or something like that, right?
Yes.
So wouldn't this kind of objective function be kind of a function of your application, meaning that this one is just an infrastructure that you are creating for a more kind of at a higher level application, right? Meaning that there are some maybe requirements, for example, for that airplane design or something, but it can have some impacts on your objective function. Right?
Not necessarily for this objective function, it doesn't have any impact on it. Because what we are concerned with is that whatever your application is, whether CFD simulation or any other type of simulation, you want to have good quality measures to reduce the error in your simulation, right? And the result of the simulation. So we are concerned with providing that good quality mesh to ensure that if there is an error, it's not coming from a bad mesh.
So no matter what the application is, always having a more kind of for a better mesh for better.
Yes.
Yeah, I guess I mean my final question, and I guess that's what I said. This one, there is no guarantee in convergence or anything, right? So we are just fixing locally.
Yes. And we see if there are any oscillations. Because at the end of each run, we are looking at the worst quality. The worst quality of it. So,
Thanks.
no problem.
Thank you. Any other questions? If not, thank you, Mike.
Thank you very much.